So this is the web. So this top portion we call it as flange. The center portion is the web portion. The outer part is the flange portion. The outer flange and the inner flange, or we call it as top flange and the bottom flange. Okay, and center we call it as web. It is right side. So the thickness of the flange is 11.5. Width of the flange is 100. The total depth of the flange from outer to inner flange, the total depth is 225. 225. And thickness of the web is 7.5. Next. So it is a simply supported beam. So it is simply supported. The ends are supported. Okay. For the span length, the length of the beam is 12 and maximum stress acting on the beam is 80. So it is a simply supported. We have kept the support at the ends. The length of the beam is 12 mm. Length of the beam is 12 mm. Okay. And there is one more portion. The maximum stress acting on the beam is sigma maximum, it is 80 Newton per mm square. Then there is a load. The load acting on the beam. So we have a load W. W is the load acting on the beam. So this load is at a distance 4 meters. 4 meters from any of the support. You can take it to either right hand or left hand. It is at a distance 4 meters. The load acting is at a distance of 4 meters from one of the support. You can take it from A or B. So this is the problem statement. This is the problem statement. I need to find this unknown weight W. W you need to find. So this is the symmetric section. Symmetric section. So I'll whatever the section. So if it is a symmetric section or it is not symmetrical, you need to find a moment of inertia. The rule to find moment of inertia, you can apply the second rule for a symmetric section also and unsymmetric section also. If it is a symmetric section, so you can consider this as a rectangle, this outer as a rectangle portion. So you know what is the moment of inertia for a rectangular portion. So if it is a rectangular portion, so this width is what is taken D. So this width is B. The moment of inertia for a rectangular portion, it is given by what? Last class.
BDQ by 12.
Is BD cube by 12, right? For a symmetric section, it is not a problem. So if it is a symmetric section like this, if you take any axis, so if this is a axis for this center portion, and this will be the axis for the other portion of the flange. Okay. So now let us consider this as a complete, just for a reference. So this complete as a one rectangular portion. So if it is a rectangular portion, so let us find the moment of inertia for this I section. So let me consider it as a total rectangle and find moment of inertia for this outer rectangle. I is equal to this outer rectangle. Okay. So it is, what is the depth? Depth is this height. It is 225. 225. This holds good for only symmetrical section. So after completing this problem, I'll tell how to find it for in general if it is not symmetrical. Okay. Depth is 225 here, right? So the width of this rectangle. So just imagine it is complete rectangle. Okay, I need to find it for only this I portion, I section. To find that, I will find the moment of inertia for this complete section. So which is having the depth 225 and width is 100. Then I will minus for this portion. So if I remove this, if I minus the moment of inertia for this portion, so I will get the moment of inertia for the I section. Okay, it will be moment of inertia for the outer rectangle, that is I1 minus I2. I2 is for this, whatever the portion that is inside. So I have hatched it right. So if I subtract this portion, moment of inertia, and this two portion, so I will get the moment of inertia for the I section, right? So this is the method that can be adopted for symmetrical section. The moment of inertia is, this can be adapted for only symmetrical section. I'll tell once again. So I need to find the moment of inertia for this I section. To find that, so let me find the moment of inertia. Consider this as a only outer boundary you just consider. Considering this as only rectangular. So this outer rectangular portion, I will find the moment of inertia, that is I1. And if I subtract the moment of inertia for these two portions, whatever I have hatched it here. So if I do that, that is I2. Then I subtract, I will get the moment of inertia for I section. Okay. So now let me find the moment of inertia first. That is moment of inertia for the I section. This is for symmetrical I section. So that is I is equal to I1 minus I2. So you consider this as this is only for your reference. So you need not to write this. So you can directly. So this is portion 2, and this I is portion 1. Okay. So now, what is the moment of inertia for I1? Is I1? It is general. So it is nothing but the outer rectangular portion. So I am not going to write any equation. It is direct. So what is this? What is the B for this? What is the width and what is depth? The width is how much? For this rectangle, it is complete. First portion. It is B is how much? B is 100. Depth D is 225. So I1 is BD cube. B is 100 into D is 225. BD cube by 12. So this is I1 minus. What about I2? So I want to find the moment of inertia for this two sections. These two sections. So what is the, so consider this as one full rectangle. So this portion from here to here. Only this portion as a rectangle. So I want to find the width of this portion. Width of this portion. So what is the width of this? So it is 100 minus this web width. What is that? 7.5 will be the width. This portion. So it includes in the I section. So if I want to neglect this, I want to find the moment of inertia for this only the hatched portion. So it is 100 minus 7.5 will be the width. So what about this height or depth? This depth will be 225. 225 minus 11.5 minus 11.5. I will get this height or depth, right? So what is the B for this second portion? It is 100 minus 7.5. What about D? Depth is, what is the depth of this portion? It is 225 minus 11.5, 11.5. 225 minus 11.5 minus 11.5 whole cube divided by 12. So that will get you the moment of inertia for, this is only for symmetric section, symmetric I. So if it is not symmetrical, then method is different. So what is moment of inertia for this section? What is I? Find out. How much? For only symmetric section. After completing this problem, I'll show the method to find the moment of inertia for unsymmetrical section. You can apply that for symmetric section also. But for symmetrical section, this is the easiest method. You can compare your answers by the second method also. So what is I?
3.18 10 to the power of 7.
You just keep it for 3 or 4 digits. 3.1. How much?
Into 10 to the power of 7.
If it is 10 power 6, 7 like that, at least you keep it for 4 digits. Since it is 10 to the power of 7, so how much? 3.1, 3.18, something you told, right? How much?
38138.
38138 into 10 power 7, mm to the power of 4. Okay, now you just, it is another regular problem like last problem. So only this moment of inertia it is different. It is a simply supported beam. You take the reaction force as RA, RB, just like regular simply supported beam. Find out what is RA and RB to find the reaction force. Find the reaction force. Reaction forces. So that is, take moment at one of the point. Take moment at A. The sum of moment at A is equal to 0 at A. So when you're taking sum of moment at any of the point, you can take clockwise movement is equal to anti-clockwise movement. So that is, we are going to take moment at the point A. So what are all the forces acting with respect to point A? One is RB, another is W. So RB is at a distance 12. It is anti-clockwise. One is anti-clockwise, another is clockwise. So you can equate both. So one will be plus, another will be minus, right? So you can take clockwise will be equal to anti-clockwise. That is RB into 12, W into, so it is 12 minus 4, 8, right? So RB into 12 will be equal to W into 8. So what is RB? RB will be equal to 8 by 12 into W. So 8 by 12 andre 4 ones are 2. It is 2 by 3, 2 by 3 W RB. So you know that the reaction force RA plus RB will be equal to W. The sum of RA plus RB, by under equilibrium condition, whatever the forces going up will be equal to the forces coming down. So to balance at equilibrium, RA plus RB is equal to W. So find out RA. Find out RA. So RA will be equal to W minus RB. W minus 2 by 3 W. So 1 minus 2 by 3. 1 minus 2 by 3. So it is RA is 1 by 3, right? So RA will be 1 by 3 W. So W is the unknown I want to find. Then you find the maximum. You find the maximum moment. I'll drop this moment of inertia. So next you find maximum moment or bending moment. So for a simply supported beam with point load, the maximum moment will be acting at the point of the load. So this you need to keep it in your mind. So for a simply supported beam with point load, the maximum moment will be at the point of load. So at this load you can calculate moment from both the ends. So from end A and from end B. So whichever will come maximum that you need to take, or the other method. So the maximum moment will be at the point with respect to the maximum distance of the support. So, which support is at a maximum distance? So here support A is at a maximum distance. So moment is force into distance, or you can calculate the moment with respect to both the supports, whichever is maximum that you should take. So with respect to this point load, there are two moments you can take. One is with respect to A, another with respect to B. So with respect to A is RA into distance is 8, and with respect to B it is RB into distance is 4. Since the maximum moment acts with respect to the maximum distance from the support, so the maximum distance will be with respect to point A. The maximum moment will be at point A. You can take it both. If you're confused, you can take it both. So you can write the maximum moment acts at the point of load. For a simply supported beam, with point load, the maximum moment acts at the load point, or at the point load, So to calculate that moment, this maximum moment, consider a support which is at maximum distance. So you're taking the moment with respect to maximum distance, you will get the maximum moment. So the maximum moment is M max. M max will be equal to, so which support is at a maximum distance is RA. So RA. So it will be RA into, the distance is 8. 4 minus 12, it is 8. So what is RA? RA is 2 by 3, 1 by 3 W. So it will be 8 by 3 W. M max will be 8 by 3 W. Or there will be two moments. So with respect to RA, it will be, you take it as moment 1, RA into 8. With respect to RB, you can take it as moment 2, it is M2, RB into 4. So it is understood. So whichever is maximum, that is taken as maximum moment. Or you can directly take it, whichever the distance is maximum from the load point to the support, that is taken as a maximum moment. Okay. So next, we have the moment equation by bending equation. So what is the bending equation? M by I is equal to sigma by y. M by I is equal to sigma by y is the bending equation as one of the bending equation, and which is also equal to E by R. So here I want to find W. I just consider only two of the expression is enough. So R, this is nothing but M by I is equal to sigma maximum by y max. Y max. So y is the distance. Y is the distance to neutral axis. So here the neutral axis for a symmetric section, it will be exactly at the center. Exactly at the center. So it is a distance from any of the fiber, that is from outer fiber. So if you consider from top to neutral axis or bottom to neutral axis, since it is symmetric section, so this will be y max. So this is the neutral axis, NA. NN is the neutral axis. It will be exactly at the center. So what is y max? So from outer fiber, so it will be equal to, the total depth is 225. It will be equal to half of this. So y max will be equal to y max is 225 by 2. So m is nothing but m max. So maximum moment. So you calculate, you substitute all the terms here. So sigma max is 80, it is given in the problem. So y max we know, m max is in terms of W, and I, moment of inertia, is also in terms of, where is I? I is here. We have calculated moment of inertia, substitute and find out W. So substitute in this expression, m by I is equal to sigma by y. So you substitute all in this equation. What is the load acting on the beam with respect to this maximum stress you need to find. So if W was given, the stress will be the unknown. The stress you need to find in that case. So here, just make sure that the units are in. So here it will be in meter only. In meter, you just convert here. M max, it will be in meter. So here the section it is in moment of inertia, it is in mm. So convert that to mm here. You should convert. So one of the units is in meter, another unit is in mm. So don't substitute directly, it will be wrong. So make sure that you convert this to mm. So it will be 8 by 3 W into 1000. It will be in mm. Maximum moment. You convert to mm. And also here y maximum it is directly is in mm, it is in mm. So make sure that it is in mm. Then sigma is in mm only. You just need to convert this to mm. So now it will be in Newton mm. Units, just make sure you follow in single units.
Eight point three kilonewton.
8.3 3 some ಮುಂದಕ್ಕೆ kilo just keep it to some three digits. So whenever you're keeping
8.349 kilonewton.
349 kilonewton. Okay. So in some problem they will give the load. Load if it is given, we should be finding out sigma maximum will be unknown. Okay. So these are with respect to symmetric section. The only thing how to calculate the moment of inertia. Other thing it is similar to the previous problem, what we solved in last class. So now let me explain how to find the moment of inertia in the second method. That holds good for unsymmetrical sections and also as well as symmetrical sections. So you can compare this answer moment of inertia whether it comes same or what. So this completes this problem. So this is only for your note, additional thing, so that you can use it for the next fourth problem to find the moment of inertia. Next, that has to be done by you. Okay. So for the same sketch, I will show how to find the moment of inertia. Next method. So this completes this problem. It is W is 8.349 kilonewton. Can consider the same. So just for your note, you can write it as a reference note. So any sketch, if it is given, if it is unsymmetrical, first with respect to bottommost fiber, and you take some reference. You should take some reference axis. So to the bottommost fiber and to the left. To the section. So I'll be marking it as y-axis, and the bottommost fiber. Let me mark it as x. Okay. The first step is you should mark the reference axis. Take a reference axis to the bottommost fiber, and to the leftmost fiber you take it as y-axis. To the bottommost fiber you take it as x-axis. Okay. So this is symmetrical section. This is symmetrical section. So here you mark down the neutral axis. So let this be the neutral axis. NN. I'll name it as NN as a neutral axis. So whenever the beam is straighter beam, the neutral and the centroidal axis will be merging. So unless it is a centroidal axis will be in the same line. For us, the neutral and centroidal axis will be in the same line. So let me mark the centroid point as C only. C. Okay. For a straighter beam, if it is for a curved beam, the neutral and centroidal axis will be shifted by certain eccentricity. For a straight beam, it will be on a same line. So let me mark that centroid as C. Okay. So now. So for all the rectangles, so consider as a separate rectangle. So let me call this as first section. So this as second section. So this bottom flange, I will call it as 1. The web portion, I will call it as 2. And the top flange, I will call it as 3. Okay. See. So for the x-axis, it is same as a neutral axis. It is same as a neutral. It will be exactly at the center. It will be same as a. And for the top flange, this is the axis. This is the axis. And for all these three, first and second and third, so this will be the central axis. It is same. The y-axis is same for all the three portions. It is exactly at this line. So now let me find the location of this point C. Location of this point C. The centroid I need to locate. So the centroid will be located at a distance x bar and at a distance y bar. So with respect to the reference axis. So with respect to x-axis, so I am going to measure this. Y bar is nothing but this y maximum. Okay, this y bar. With respect to x-axis, I will get y bar distance, and with respect to y-axis, I will get the x bar distance. That is the location of the point C. The location of the point C, so I can measure. Okay. So what is x bar? So x bar will be equal to, so what is the distance of this x bar? So since for all the three sections, the location it is exactly at the center. Since it is symmetrical, so for all the three sections, the y-axis is passing on the same line. For first flange, this flange, top flange, bottom flange, as well as the central web, this axis line is exactly at the center. So x bar distance is same for all the flange. For all the rectangles, this distance will remain the same. So what is this x bar? Since it is symmetrical, so this is acting at a, this is the total distance of the, this is the total width of this section. The total width of this section is 100. So x bar will be equal to, it will be exactly 100 by 2. 100 by 2. Right? So similarly, y bar will be, we should calculate y bar for all the sections. So since it is symmetrical, since it is symmetrical, since it is symmetrical, so y bar, you just calculate y bar. So since symmetrical, if it is there, it is not a problem. It can be easily calculated. So for unsymmetrical section, in the next class, I will show how to do it. So for so y bar distance, it will be 225 by 2. So this is the location of this point C or point C on the neutral axis. So this is for symmetrical sections. Okay. So how to find next moment of inertia? So moment of inertia, this is with respect to x-axis. So this is Ixx we call it. With respect to this x reference, the moment of inertia of this I section, this will be equal to moment of inertia of this rectangle bottom flank plus moment of inertia of this second web and this moment of inertia of this top flank. So Ixx will be equal to moment of inertia, that is I1 plus moment of inertia I2 plus I3. Moment of inertia for this bottom web, bottom flank, central web, and top flank. So for IR, we can call it as with respect to XX, so we can call it as IX1, IX2, IX3. This is the total moment of inertia with respect to x-axis. So individually, I need to find the moment of inertia for this bottom, top, and central web. So let me find out what is the procedure. The moment of inertia is calculated. So with respect to x direction, so it is equal to moment of inertia of that particular section. So we call it as Ig1. So what is the regular equation? So it is the moment of inertia for this rectangular section. The equation to find the moment of inertia with respect to x-axis is moment of inertia for this section, for this particular section, okay, plus area of that section. So this is with respect to x1 plus area of this section, into h1 square. h1 is the distance from the centroid of this section to the neutral axis. So this is h1. h1 is the distance from centroid of this section to the neutral axis. The centroid of this section. The centroid of this section, since it is only rectangular section, the centroid will be exactly at the center. This will be at this point. So distance from this centroid to the centroid of the whole section. Centroid will be exactly at the center. So now you calculate the moment of inertia for this particular section, Ixx1. So this is complicated. In case of symmetrical section, the first method is better. If it is not symmetrical, you follow. Ix1 is how much you calculate. So Ig1 is moment of inertia for only this section. It is what? BD cube. That is B1 cube by 12. So area of this section it is A1. A1 it is area of the rectangle. So width into this depth. So width is 100, depth is 11.5. So that is B1 into D1 is the area. H1. H1 is the distance from this centroid to centroid of this section to the original centroid of the I section. Okay. So H1 is how much? So Y bar is how much? 225. 225 minus 11.5 by 2. 11.5 by 2 will get you this H1. This 2 Y bar is how much? 225 by 2 minus 11.5 by 2. So this is for first section. Similarly, you calculate for second section with respect to the neutral axis and centroid. Okay. For the second section, since the neutral axis and centroid both are merging with respect to the whole I section neutral axis, and this section, the second web section neutral axis are coinciding with respect to each other, since the H2 will be equal to 0. H2, there is no distance. There is no H2. Since it is coinciding on this axis itself for the second section, plus centroid of the section will be 0. So similarly, Ix2 for this second section, only we are considering this part of the section. So what is the width of this section is 7.5, 7.5, and this depth of this section is 225 minus 7.5, 11.5. So that is the depth. So same for the second section, moment of inertia of that particular section Ig2 plus area of the section into height of the section square. So this is the equation. This you need to remember to calculate the moment of inertia. This is particularly for unsymmetrical section. It also holds good for symmetrical section. So to calculate x bar, y bar, it is different with respect to unsymmetrical section. That will tell in the next. So here, what is Ig2 is the moment of inertia for this particular rectangular section. It is width is 7.5, depth is 225 minus how much is this? 10, 20, 23. 225 minus 23 will be the depth. So it is equal to B2 D2 cube by 12. Same B2 D2. So this portion is 0. H2 is 0 into 0. So this entire will be 0. Both the axis and the centroidal axis and the neutral axis for the original next we calculate for Ix3 for the top flange Ix3 will be same equation. So it is B3 D3 cube by 12 plus B3 D3 is the area of that section into H3 square. So what is H3? H3 is this is the centroidal axis for this particular section. It is the distance from the centroid of that section to the neutral axis or the centroid. Okay. So this distance will be H3 from this particular centroid to the original centroid of this whole section. That is H3. So H3 is how much? Almost same. I think H1, H3 will be same for this section. Right? Since it is a symmetrical, it will be same. Okay. So you calculate this, then afterwards you add all this, so you should get the same answer with respect to x-axis. The moment of inertia it is g. So this is with respect to x-axis. So since all the x-axis for a particular section is different, so this moment of inertia will be different. So with respect to y-axis also you can calculate the moment of inertia with respect to this y. So with respect to y-axis, since all the y-axis for this section are coinciding, so the moment of inertia for y-axis will be V1 D1 cube by 12 plus V2 D2 cube by 12 plus V3 D3 cube by 12. Then all the sections centroid is on the same line. So it is nothing but a general expression for y-axis. So we are only considering the moment of inertia with respect to x-axis since the beam is bending with respect to the vertical. So that is with respect to x-axis. We are going to consider the moment of inertia only with respect to y-axis for unsymmetrical section as well as a symmetrical section. So we consider only I-axis with respect to the x-axis. It is the x reference. So when you just calculate all this and add it, the answer should be same as what you got earlier. So that is what is the answer 3 point something into 10 power 7 you told. It should be same. The moment of inertia with respect to x, I-axis. You do it, you just calculate, you will come with same answer. So this is the method to calculate moment of inertia for unsymmetrical section. So don't use it for symmetrical section. For a symmetrical section, you use that same what we done in the problem. So that is simpler. Okay. For unsymmetrical section, you follow this.